Today we're going to talk about a case study in mobile analytics. We are specifically talking about predicting customer churn for a mobile subscription service. Our problem statement, like I said, this is a case study for using deep learning in the context of mobile analytics. I work for this particular CPG weekly subscription service. We're attempting to predict customer churn for the mobile subscription service. Um, Customer churn, for those that aren't aware, means when a customer leaves. So we're trying to predict when a customer will end their subscription. This company has a goal to detect which customers will churn from their subscription on a weekly basis. This is a important thing because if we can detect this ahead of time, we can interact with the customer in a positive way to stop them from doing so via some sort of marketing campaign, or maybe even if we give them credits of some sort to stop them from leaving the service. The company's service is given via a mobile app, and what makes this particularly tricky is that a customer may end their subscription and then come back. Therefore, customer churn is defined as the customer ending their subscription in a particular week. So this data is not publicly available, but it is included in the project files, so please download the data from the project files. We have behavioral data collected for customers on a weekly basis that reflects the customer subscription analytics and mobile behaviors collected up until the current week, such as order edits, ratings, and visits to the menu page. So this data is a small subsample from the actual data from the CPG subscription company. This data also only reflects values from a few years ago, and this is just to protect proprietary information and things like that. So a couple things. The main parts of this project is using SMOTE to help out with imbalanced data. And we train a sequential multi-layer model architecture while checking for overfitting when using the synthetic data. The overall goal is to have the network perform propagation to learn low-level features of the customer analytics as it relates to customer churn. Here we have the hardware that was used for this project, but really I think any EC2 instance should be able to handle this. We did not have any problems with speeding up training or anything like that. This is our software that we used. We used Python 3.7. Scikit-learn is used for various machine learning tasks like splitting the data, doing classification reports, and things like that. We also have imbalanced learn that's used to perform SMOTE. And just so everyone knows, SMOTE stands for Synthetic Minority Oversampling Technique. We'll talk a little bit more about that in a second. We use TensorFlow and Keras to perform deep learning, Pandas for data manipulation. Keras Metrics was a nice package that I found to help track precision and recall over every epoch. And we use Matplotlib and Seaborn to do visualization. So you want Matplotlib 3.1.0 in order to get it to work with Seaborn correctly. I had the latest version of Matplotlib, and some of my plots were cutting off and it just didn't work right, so make sure that you use 3.1.0. And so some of the lessons that we learned, imbalanced data is hard to learn from as the model may not be able to find the correct patterns in the data. Looking at customer churn as a classification problem is very important. Typically, you look at cohort retention and the percent of customers that leave on a weekly basis, and a lot of success has been had using those techniques. But if you split it up into individual observations, it becomes a classification problem, and that way you can kind of hyper target customers into different marketing campaigns, right? So if a customer is classified as likely to churn, then you can kind of circumvent that and put them into a marketing campaign to stop them. So another option to kind of deal with imbalanced data is weighting the loss function. And we tried this out, but ultimately we found synthetic data was more useful for this particular problem. And we also tried undersampling the majority class. But again, SMOTE by itself was the most fruitful in this particular problem. Another thing that we learned was that Dropout is typically chosen between 20% and 50% of the features to be hidden from the model, but we found the most success using 10%. I think this is because with a small number of features in most analytics projects, higher dropout is not as optimal. And so here we have a short tutorial on how you can download all the correct packages to do this project. And here we simply import our data. Having a look at the different features available, we see most are either float or integer. Churn is obviously Boolean, as we're doing a classification problem here. And here we dig into the different features we have. So by definition, churn is whether or not a customer churned the following week. So if you think about our observations as a point in time t, all of our features are collected up until t, and churned is collected as forward-looking. So churned happened in time t plus 7. So we have the lifetime of customer's current subscription in weeks, the number of subscriptions a customer has had, the number of weeks between a customer's previous subscription and their current subscription, the sum of pause weeks for a customer, the number of weeks since a customer first started their subscription, the total number of edits a customer made to their orders, the average number of items in a customer's weekly order, the average value of a customer's orders, the average number of unique items a customer orders, the sum of ratings a customer has made, the count of ratings a customer has made, the total number of orders a customer has skipped, the total number of visits to the menu page a customer has made. We also include census data for a customer's zip code. We have population for that zip code, mean salary for that zip code, and median salary for that zip code. So taking a look at the data, we see that we have some nulls here, which we'll talk about in a second. And here is some descriptive statistics of the data. So the number of rows in the data is 200,000. So if a row has a count of less than 200,000, then it has nulls, right? And having collected the data myself, I know that we don't want to make assumptions about population and salary related fields. So we remove these rows that don't have these values, and we can assume that all other values can be filled with 0. So if we take a look at the correlation plot, we can see the correlations between the different variables. But just based off definition, some of these are going to be very correlated, such as like mean and median salary of the zip code, such as AOV and order items, and some of them not going to be related at all. But very interesting to look out for sure. In here we see the balance of our classes. We see that 7% of customers on a weekly basis will churn and 93% won't. This is very imbalanced. And so we use SMO to create synthetic data for our minority class in order to balance our data. So SMO uses k-nearest neighbors to create the synthetic data. And it also has some TensorFlow built into it. So this is also a good showcase of another deep learning related technology. We use a sample strategy of 1, meaning that we want a perfect ratio between our classes. Here we split our train, test, and validation sets, split of 70, 20, and 10. We do standard scaling on the X-train data set. And then we take that transformation and we apply it to our validation and our test sets. Here we do some one-hot encoding. And here is our model architecture. We use a sequential model, and we have 3 dense layers of size 128, and we add dropout layers in between, and finally we have our flattening layer at the bottom. We found that these particular parameters were most optimal as after doing a lot of different tuning um, to get pretty much the most optimal model that you can possibly get. Here's our model summary, which will kind of show you how many parameters and trainable parameters are within the model. And here we will train and test our model. It's important to note that we use precision and recall as accuracy measures because in any classification problem, you want to be able to track precision and recall. Um, a model that has 95% of class A and 5% of class B could potentially classify all observations as class A and still have 95% accuracy. So we use precision recall to kind of circumvent any misunderstandings, and we use KRS metrics to be able to track this throughout epochs. Here we compile with the loss function of binary cross entropy, and our optimizer is RMS prop. And here we fit our model over 50 epochs. So after fitting the model, we see good results in loss and 35% loss, test loss, and 86% test precision, 77% test recall, and 82% test accuracy. Based off our training and validation loss plot here, we don't believe that this model suffers from overfitting. And finally, we see here our classification report, which shows our precision recall and F1 score for both classes. We see that the model does a good job of balancing. So SMOTE was very successful here. And we also see accuracy measures as well, 83% across the board, which was pretty interesting, but very good nonetheless. F1 score, for those that don't know, is the harmonic mean of precision and recall, which gives you a more holistic view of the two metrics. And here we take a look at a visualization of a confusion matrix, which shows models how they fall into different classes, or the observations how they fall into different classes as predicted by the model. A perfect scoring model would have everything across this diagonal. We have some errors here, of course, as is with most models, but overall this was pretty successful. And so just a little bit of background on customer churn. Typically you have models that predict a customer's cohort and percentage of that cohort that churns out on a weekly basis using some sort of hazard function or survival analysis. People use power regressions in the past, but ultimately we find that these old school techniques are good for the aggregate of predicting when customers are going to churn. But if we want to do hyper targeting, a classification problem like this is usually the best way to go. And it's awesome that we were able to get such good accuracy metrics across the board for both classes so that we can do hyper targeting within marketing campaigns and things like that. And that's all that we have. Thank you for watching.